Many of the potentially habitable exoplanets you've heard of, such as Proxima b or the TRAPPIST-1 system, orbit red dwarfs, the smallest and most common type of star. Red dwarfs are very small and dim, so planets have to orbit much closer to them to have habitable temperatures. For comparison, all 7 of TRAPPIST-1's confirmed planets, from the supermercury TRAPPIST-1b to the very cold TRAPPIST-1h, orbit their star closer than Mercury orbits the Sun. Red dwarf systems are often more comparable to the moon systems of Jupiter and Saturn than the arrangement of planets in the solar system. Because of this, many planets orbiting red dwarfs are tidally locked to their stars. This means their day length is exactly equal to their year length, resulting in one half of the planet in permanent daylight and the other half in permanent night. This could have serious implications for the habitability of Earth-sized planets around red dwarfs. For example, you've probably heard of the popular idea that tidally locked planets will have scorching hot deserts on the day side, massive frozen ice sheets on the night side, and only a thin band of twilight in the middle where habitability is possible. This idea is most likely incorrect. Like all things in astronomy, tidal locking is far more complicated than it appears at face value. As we'll see in this video, you can get tidally locked planets with lush, wet, temperate day sides, relatively warm night sides, and hundreds of other unique scenarios. I've gotten many comments saying that it's impossible for tidally locked planets to be habitable, but that is simply untrue, and while they will have unique challenges, there are a few specific ways where a planet being tidally locked may actually be better for life than a planet with a day-night cycle. So the question we'll be answering in this video is how exactly a planet being tidally locked affects habitability. We'll talk about climate, oceans, atmospheres, and a lot more. Welcome to episode 2 of the Habitability of Red Dwarf series, where we'll be going in depth about what exactly it would take to have a habitable planet around a red dwarf, and how likely it is. Episode 1 was about the cosmic shoreline and atmospheres, and I highly recommend you watch that one before this. For a quick summary, it's far more likely than you may think for an Earth-sized planet around a red dwarf to have an atmosphere, and red dwarf flares are actually only one factor in whether or not a planet around it has one. So for this video, we'll be skipping talking about atmospheres and assume the tidally locked planet in question has one. Whether or not it has oceans of water is the subject for another video, but for this video we will again be assuming it does. The first thing you need to understand about tidal locking is that it comes in several forms. For example, Mercury is tidally locked to the Sun, but it doesn't have a permanent day or night side. This is because Mercury is locked in a 3-2 spin-orbit resonance instead of a 1-1, so it rotates exactly 3 times for every 2 orbits. Tidal locking is, in essence, a synchronization between a planet's rotation and its orbital period. It doesn't always have to be 1-1, and the 1-1 ratio results in the permanent day and night side. There are many things that can slow down or stop a 1-1 tidal locking, or even tidal locking in general, from occurring. The first thing is an elliptical orbit. This is probably what happened for Mercury. If a planet's orbit is eccentric, it speeds up at its closest point from the star and slows down at its furthest. The planet can't just magically spin faster or slower like that, so if its orbit is eccentric enough, while a 1-1 tidal locking is technically possible, the star would move around the sky so much that a pretty decent chunk of the planet would have something at least resembling a day-night cycle, where the star hops up and down. Which is why Mercury's in a 3-2 resonance instead of a 1-1. However, a more eccentric orbit has different effects on habitability that are beyond the scope of this video, so we will be assuming that red dwarf planets have mostly circular orbits. When tidally locked planets were first talked about many decades ago, many people thought that such a harsh difference between the day and night hemispheres would result in a similarly harsh difference in climates. Some even suggested that planets like these could not have oceans or atmospheres, because it would all condense as ice on the night side and get stuck there. Even if an atmosphere was possible, then surely the day side would be an uninhabitable desert and the night side a frozen wasteland. This idea has remained popular to this day, despite the fact that modern data and simulations show that it's pretty inaccurate. This is just not how heat transfer works for most planets. As a very basic science lesson, heat flows from hot areas to cold areas. This is seen in water freezing outside on a cold day. It remains true on every planet in the universe, including tidally locked ones. Planetary atmospheres transfer heat around, that's why weather happens. Modern simulations have shown that, on a tidally locked planet, an atmosphere significantly thinner than Earth's would still be thick enough to transfer enough heat from the day side to the night side to prevent the atmosphere from freezing out and the planet becoming airless. An atmosphere similar to Earth would even result in temperature variations very similar to the ones we experience on Earth today. And oceans transfer heat as well, that's why currents happen. With oceans, the night side water might not even freeze, and remain liquid despite not being in direct starlight ever. So permanent water oceans can absolutely exist on the night side of a tidally locked exoplanet. Of course, if the atmosphere is thin enough, this scorching desert, frozen wasteland scenario may occur. But those planets wouldn't have had a chance of being habitable anyways, because the atmosphere would be too thin for life. For Earth-like planets, tidal locking doesn't really seem to be that bad. So moderate temperatures can exist on the night side, but what about the day side? Well, again, modern models show that it may not be that bad. For tidally locked Earth-like planets, a permanent cloud layer near the subsolar point, the hottest area of a tidally locked planet, may form. These bright reflective clouds will reflect the most intense sunlight away from the planet, allowing for moderate habitable temperatures to exist on the day side as well as the night side. Though this cloud layer is expected to only form on warm planets on the inner edge of the habitable zone. But for these planets, this cloud layer may actually prevent a runaway greenhouse effect from happening, and keep moderate temperatures on a warm planet on the inner edge of the habitable zone. For cooler planets on the outer edge of the habitable zone, this cloud layer would not form, allowing for direct sunlight on the subsolar point. This would warm up the planet and prevent it from becoming frozen over. Essentially, if you made Earth tidally locked around a red dwarf right now, it seems not much would really change. You'd still have warm but survivable temperatures on the day side, and cold but survivable temperatures on the night side. Ocean and atmospheric currents would prevent the day side from becoming unbearably hot and the night side from becoming unbearably cold. In fact, this type of climate may actually be more stable than the one we have, leading to more constant surface conditions for any life that may exist. So far, this all sounds pretty good, but there are still a few problems. For example, the same heat transfer that prevents a runaway greenhouse or global freeze-over may create hurricane-force winds across the Terminator line, making the band between day and night uninhabitable. I actually used to believe this myself. However, yet again, modern estimates have shown this is likely not true for many planets. For an Earth-like planet, Terminator winds may only blow about 5 to 15 meters per second. That's basically a stiff breeze, and definitely not a hurricane. The biggest effects this would have would be significantly more wind erosion on mountains near the day-night boundary. While these adjustments will be generally true across a wide range of planets, the exact numbers will vary wildly depending on each planet's specific temperatures, orbits, and atmospheric conditions, which is why I haven't included many specific numbers so far. The specifics of this also depend on how quickly the tidally locked planet rotates. Some red dwarfs are large enough that the habitable zone planet will have orbits and thus day lengths of a few weeks or more. This will affect the planet's climate, as for example, on a slow rotator, the Coriolis effect will be much weaker, leading to significantly weaker ocean and air currents. Interesting, this will also affect continental drift. Something I've talked about in a few past videos is that plate tectonics is a major reason Earth is still habitable today. It's extremely important for the carbon cycle and prevents a runaway greenhouse effect from beginning. If you want to see what happens to an Earth-sized temperate planet with no plate tectonics and a fully solid crust, look no further than Venus. While it may be possible for a planet to be habitable without plate tectonics, such as early Mars for example, I personally think that plate tectonics is most likely necessary for a planet to remain habitable for billions of years. And plate tectonics may potentially be interesting on tidally locked worlds. For example, due to tidal forces the planet experiences, the crust will slowly over time be dragged toward the substellar point, resulting in the largest land masses being concentrated on the day side. Or in simpler terms, whatever continents form on the tidally locked planet, that planet will reorient itself until the continent is as close to the substellar point as possible. So it seems that scorching hot deserts on the day side are probably possible, and even potentially what the majority of tidally locked ocean planets have, assuming those planets have active plate tectonics and methods to form continents. As I just mentioned about Earth, plate tectonics are important for stopping a runaway greenhouse effect. This is because the constant recycling of rocks allows for carbon to be weathered and basically sucked out of the atmosphere. This process is more efficient when the rocks are hotter. So on a planet where all the large rocks never see darkness, this weathering will be dramatically faster than it is on Earth. If Earth was tidally locked around a red dwarf like this, it's estimated that atmospheric CO2 levels would gradually drop by a factor of 10,000 as the continents converge on the substellar point. At first this may sound like a good thing. Earth-like planets that are tidally locked may have a more difficult time turning into Venuses. However, it's a double-edged sword. Photosynthesis requires some level of carbon dioxide to happen, and that little carbon could be disastrous for any plant life. And the climate effects wouldn't be great either. Poor ocean circulation caused by continents under the substellar point would make the day side hotter and the night side colder, since the heat transfer would be less efficient with massive continents in the way. However, all in all, this would actually cause the planet as a whole to cool significantly, maybe in some scenarios to cause ice caps on the night side. And then, when that continent substellar point inevitably breaks apart, the opposite occurs. Carbon is rapidly released back into the atmosphere, the temperatures rise sharply, and the ocean circulation improves and temperatures become more temperate, until the next continent waters over to the substellar point. So to be clear, all this does not affect planets with global oceans or planets without active plate tectonics. But assuming tidally locked planets do have plate tectonics like Earth, it may harm habitability. So this sounds like a pretty unstable climate and is a major issue for the habitability of tidally locked planets. Planets with atmospheres around 20% as thick as Earth may have it especially bad. This weathering could cause a drop in pressure so significant it leads to total atmospheric collapse, similar to what happened with Mars. This is made worse with all the usual climate effects normal planets have, such as ice reflecting more light back into space, cooling the planet and making more ice, until it's a snowball is one example. And as mentioned, planets with substellar continents will be colder, and that could allow for significant ice buildup on the night side, which could trap water and further make heat circulation worse, leading to a colder night side with more ice, until you actually do get a planet with barren desert day sides and icy wasteland night sides. Planets like that may still be possible, though under some pretty specific circumstances that absolutely do not apply to every planet, or even most of them. So, tidally locked planets have a few things going for them. Assuming continents on the day side don't cause problems, they could have very stable, moderate environments on both the day and night sides. Clouds may form under the substellar point, cooling the planet further, and there are scenarios where runaway greenhouse effects can be prevented in ways they can't for planets like Earth or Venus. However, should continents cause problems on the day side, it may cause drastic climate variations that tip the scales in the favor of uninhabitability, causing the collapse of photosynthesis, or in extreme cases, the collapse of an atmosphere. But there are still a few more things to talk about both in favor of and against these planets. For one, again based on climate modeling, there are scenarios where tidally locked planets will remain habitable outside the habitable zone. For example, a planet with very little carbon dioxide or water could feasibly be much closer to the star than the habitable zone. The lack of carbon in water prevents a runaway greenhouse effect, and while most of the planet would be a barren desert, the night side and terminator line could create meltwater lakes that allowed for islands of habitability and liquid water outside the habitable zone. This could even result in the popular idea of a habitable twilight zone with an uninhabitable day and night side. However, we are talking about red dwarfs, and the closer a planet is, the harder of a time it will have holding onto an atmosphere, so how common these types of planets is would be a mystery, and may be generally limited to super-Earths. So the popular idea of tidal locked planets having barren deserts, icy wastelands, and a habitable terminator, while inaccurate for the vast majority of planets, is technically possible under highly specific circumstances. But it will probably be rare, and the majority of Earth-like tidally locked planets will not have it. The last thing I want to talk about is the effects of other planets in the system, which I find really interesting. TRAPPIST-1 specifically is a good example. Due to the gravitational interactions between the 7 planets, it's been proposed that TRAPPIST-1 planets may not always be tidally locked to the star, and will experience periods of tidal locking, then chaotic rotation, then go back to being tidally locked. Essentially, every once in a while, a planet like TRAPPIST-1e will just fall out of tidal locking, start rotating asynchronously, then the night side will become the day side becomes the night side, unpredictably and chaotically until it settles back down. This could also result in tidal locking scenarios that aren't one-to-one, such as a 3-2 resonance. TRAPPIST-1 is likely an extreme example of this, as its star is very small and the planets are very close together. On larger red dwarfs, these chaotic interactions would still happen, but will likely be rarer and require larger neighboring planets. And even after all of this, we've only covered half the things that go into the habitability of tidally locked planets. In the pinned comment, I'll link an article I find really good about the environments of tidally locked planets that inspired me to make this video. There's a ton in it that I unfortunately don't have the time or expertise to cover in this video, like planets with lobster-shaped temperature patterns instead of the typical eyeball pattern, and clock worlds where a few parts of the day side sometimes experience night. So I highly recommend you read that. But before we end, here's a summary of some of the complicated factors that go into the habitability of tidally locked planets. Planets with scorching deserts on the day side, icy wastelands on the night side, and a habitable terminator are possible but probably rare, and definitely not a good example of a typical tidally locked planet. Ocean and atmospheric currents on ocean planets will regulate temperatures across the planet, resulting in moderate climates on both the day and night sides, though the specifics of that will depend on many factors that will be unique to every planet. For many planets, this will prevent the night side from freezing over and allow for oceans to exist in the darkness. There will be strong winds across the terminator due to the heat transfer between the day and night side, but in most cases they will be survivable winds. The substellar point, the area directly under the star, on warm planets is expected to have constant cloud cover and heavy rainfall, lowering temperatures on the day side further. The day side will typically be the wettest part of the planet, with the terminator and night side drier by comparison. Continents will generally converge toward the substellar point due to tidal forces, which may be a problem as it will cause significant weathering of carbon dioxide and could cause issues for plants, or even atmospheric collapse in extreme cases, as well as significantly cool the planet. When the continent moves away, the opposite is true and it will rapidly warm up. But again, the specifics will be unique to every planet. Tidally locked planets will generally be more resistant to entering runaway greenhouse or snowball states compared to planets like Earth. Tidally locked planets in compact systems or with large neighbors may periodically stop becoming tidally locked, rotate chaotically, and then go back to being tidally locked, which is a subject I want to do a full video about very soon because I find that incredibly interesting. It probably has implications for any life that exists on that planet. So, in short, tidally locked planets are complicated. They have a few things that make them better for habitability than Earth, and a few things that make them worse. But really, we'll have to wait and see how common tidally locked habitable planets around red dwarfs are. And all this is still just one factor of many in the habitability of planets around red dwarfs, so stay tuned for future episodes. Thank you for watching. If you enjoyed, check out the rest of my Habitability of Red Dwarfs series.